thank you very much, Pete. And thank you all for coming here and having me here and talk to you about many things. First, I wanted to introduce what's the Barcelona Supercomputing Center for you, if you're not from around. This is the Spanish supercomputing facility. So we have the largest computer in Spain, usually, so it goes out really fast. And we upgrade it every once in a while. So last upgrade was 2017. It was the second computer in Europe at that point, with 13 petaflops of compute power. It's actually a combined machine. It has lots of CPUs, but also we have a machine with GPUs for neural trainings and so on. And in about a year and a half, we're going to have the biggest computer in Spain again with almost 200 petaflops of compute power. So what does this mean? So what do we do there? Actually, only about 1/10 of the people at the center work and supporting the users of this machine. There's about 500 researchers. This is a slightly old group photo, but there's a lot of people there working on many, many sciences. On computer science, of course, but also on life sciences and engineering, astronomy. There's energy. There's a lot of people doing climate research. And my group, we do a little bit of transversal work there because we do data analytics and visualization for many of the research projects that go on the center and also directly with some companies. And we do a little bit of a very, very wide range of things. And I had a hard time choosing one project to talk to you about. So I decided to really bore you and run you through a lot of things that we do. And the idea is that I also wanted to talk not just about the projects, but why we do so many things and so different things. I did work on quantum computing, as Pete said, but I'm not going to talk about that, actually. So this is just a flash of what's to come. So we do visualization, and we do movies with those visualizations. We do interactives. We do a lot of data analytics to support the visualization and the interfaces. And I want to divide more or less the presentation in 3 tracks. So I'm going to talk about projects that are related to data streaming first. Let's go back to Sonar 2015. So Sonar is a music festival here in Spain. It's an electronic music festival. It's very famous. It's been going on for almost 25 years. And they have now a dedicated technology fair, so-called Sonar Plus D. And it's in the spirit of South by Southwest, where they mixed entertainment industries with technology industries and try to get both worlds to talk to each other. And so we went there in this year. This is Sonar Village, the center of the Montjuic Fair. And we deployed a lot of Raspberry Pis through all the different scenarios. So the village is over there. We have about 3 devices, and we put many of these Raspberry Pis to track people's Wi-Fis. So something that you can see everywhere, more or less now. Cell phones tracking you, people tracking you in the malls. We were doing this in a little bit of an artistic approach because we wanted to let people know that they were being tracked and what people could do with this. And so we had on our booth a real-time screen like this, where we were tracking all of the different scenarios, where people were moving, where they were from 15 minutes ago. We had this in real time. And we also had the ability to track people individually through their MAC address. Actually, this is illegal to do right now because law has changed. But we were able to give people their own individual trajectories. So if this is our map of the 6 different stages, if you now think of each of these circles as a clock, then you can imagine, you can plot somebody's trajectory, like if they went into at 2 o'clock in some room, and then stayed until 4, and then they went out to another room. So we had like a little signature for everybody to see what they did through the festival. It lasts 3 days, and we were tracking about 30,000 people per day in this festival. Now, what were we doing behind this? We're just collecting data, so this was the real time. And after the festival, we did a lot of analytics, and we do a lot of business intelligence for the Sonar Festival organizers. This is just like a heat map of the expected activity at each of the rooms, by day, by time, not just the actual number of people, but the expected number of people depending on how many people were on the festival, the different artists, relationship to what they were trying to get from some people. So behind this was something that is very well known. It's like a Lambda architecture, if you want to talk a little bit more technical. So we had Raspberry Pis collecting data, and we were using Cassandra at that time for some reasons. And then data was going into 2 tracks. On the left, you had the speed track, where we're doing real-time analytics and visualization. And we had people getting these individual trajectories into T-shirts. So they could go into the booth, and they could just get a T-shirt with their activity, and a little bit of visualization and statistics on real time. But then on the right, we were just storing things like crazy so that we could have some very good and deep analytics after the festival. What we do is not go to music festivals. We work, like I said, with a lot of science and industry. So this architecture that we use for this project, we actually use it for something like this. So this is the process of treating water here in Barcelona. There's a huge plant by the south. And one of these parts is called inverse osmosis. It's a part of the industrial plant. And it has, well, most of the plants here in Spain and Europe use SCADA systems, where they can just track thousands of sensors and signals from all over the plant. What you see here is a very schematic parallel treatment of water. So you have raw water coming in from the left, and then it's divided in parallel into different tracks. And energy is being used to pump this water through filters. Okay? So this is just a collection of filters, and then you get drinkable water by the right. So what you have in the middle is a lot of machines, a lot of things that are basically generating data. There's a lot of controls. Operators are doing stuff to these things. And there's also weather, regulations, demand. There's external things that come in and influence these things. So what people want from this is usually to spend very little money on operating these plants. So maximizing euros per hour of benefit. The problem is that you have to spend money to pump the water, so that takes energy. And when the water is dirty, the filters get dirty too, and so that takes a little bit more energy, so it's more costly, so you should replace the filters, but replacing the filters also takes money. Okay, so this is a project of predictive maintenance, but also optimization of energy, because the problem is coupled. So there's a benefit, there's some equilibrium at some point where we can do the replacement of filters. Now, what we do here is exactly with the same architecture of data that we use for Sonar and other projects. We just put this here. We just have some analytics in real time for the people to look at the plant. But then we create machine learning models in order to predict when these people have to do replacements. So with this in place, it's being tested this year since January. We have, okay, I'm not going to go through all of the charts there, but we can more or less forecast the chart on the left or top. We can more or less forecast the behavior of the plant for almost 30 days, 25 days. With this, we can do some predictions, and they are more or less 20% accurate. But this is really, really good. So by the way, so we always get numbers that are much worse than that. So when you see in Kaggle, people getting something like 99% accuracy or whatever, so this is actually a huge success in the real world. So 20% error is amazing. With all these protocols in place, we have these people get about a 7% reduction in energy consumption, which for an industrial plant is a lot of money, right? So this is what we do with these structures, and we have been doing this for a few years. And now we're moving into something a little bit more streamlined, which is like, more similar to CAP architectures. So we're taking SCADA, and we're doing connections into Kafka ingestors. And then we're doing stream processing of the data and just deploying things directly into different apps. So we're just putting databases for posterior analysis. But we're trying to do the analysis in real time now, because what we want to do is a little bit more ambitious. And I'm going to plug here a couple of ongoing projects that we have. And they are more or less, this one is like about halfway between finishing. In this project, we have this architecture to try to do an automated control of the operation room of the water in the whole of Barcelona. So there's a control room. They have tons of screens. You have probably seen one of these live or in movies. There's people with a lot of experience there that they know what they're doing, and this is very difficult to train, and it's very difficult to transfer this knowledge of people into something else. So what we're investigating is the idea of transferring the optimal ways of operating these very complex control rooms into a neural network trained with some reinforced learning techniques, so that we can have this knowledge stored somewhere in some algorithm, and the company can basically have a little bit more leeway into who is operating when, and they can be prepared when there's an emergency and the people that are sitting right there don't have enough experience to deal with those emergencies. We can also do, of course, what we were doing before, which is basically early anomaly detection and so on. The other project that we're doing, it's a little bit way more nascent. We just started it about a month and a half ago. It's with Football Club Barcelona, and it's very related to what we did with Sonar. So Football Club Barcelona is, you probably heard of it. So they have this large stadium in the Les Corts neighborhood, and they also have all of the area around, where they have the store, the museum, and this area around receives about 5 million people per year. So it's a lot of people. So it's normal operation. There's more people outside the stadium than when there's a match, and there's about 100,000 people inside the stadium. And what we're doing here is giving these architectures a little twist, because they also have SCADA, so we can just plug our streams and do machine learning optimizations. But what we want to do here is also take advantage of our supercomputer, not just for training, but for operating these type of facilities. And what we do in this case is we simulate the people around. So we have agent-based models. If you haven't heard of them, it's like the professional version of The Sims or the SimCity. So you have all of these little artificial agents moving around, interacting with each other, deciding what to do, and interacting with their environment. And you use this because we want to simulate where are they going to go, how to optimize their flow. And in particular, because the stadium is going to be in renovations for the next 2 years, and they're not going to close it down. So they're going to renovate the stadium part by part, and they're going to close down a little bit section of the stadium each week. So every 1 or 2 weeks, a different part of the stadium is going to be closed down. And this changes a lot of the evacuation plans for them. So instead of having to recalculate all of the evacuation plans every week, which for an architecture studio is very difficult, we are going to get not just the parts that are closed and the plans for the stadium, but also the kind of people that are there, how many children, how many tourists are there that don't know the stadium and the area around, so that we can recalculate the evacuation plans on the same day using our supercomputer. This leads into some optimized rerouting of signals on the stadium, and we can plug that back into the SCADA systems and the controls of the stadium, and we can redirect people according to what we want to do with them. Now, let's talk about data pipelines and documentaries. So I mentioned that we are a visualization group, and this is actually how we started. I had a background in advertising, in TV advertising, doing animations. So when I went to the Supercomputing Center and I saw all this data that they had, this beautiful 3D data, I thought that we could do something with it that was much better than what scientists were doing with their commercial software. Now, the problem here is that I knew that we had to go into film tools, right? Because we wanted to create images from the data that look like this. So what we do now, many years from now, so we grew out of visualization because we were processing data, like you see. I'm going to go back to that. But what we do and what we started doing are visualizations that are for very, very, very heavy processing, and they take a lot of time for creation. And we want to create documentaries for dissemination like this one. This is called Virtual Humans. It's one of the latest ones we did. And there are actual documentaries that we submit to film festivals, and so it's typical routes that you do if you're a film creator. But we are scientists, and we work with film creators, and we work with the other scientists that work on these topics there. So what was the idea here? We started doing this because we wanted to create first hyperrealistic data visualizations. They use a supercomputer. In this case, this is a documentary for research projects that are trying to simulate human organs in order to, at some point, couple them and create a simulation of a whole human being. And these remote simulations are very, very realistic because they use thousands of computers to do their calculations. And we wanted to show and impress people to see how much realistic were the simulations by making them very, very realistic. Now, doing this at some level takes a lot of effort. So we're still on this line of going hyperrealistic or photorealistic visualizations of these computer simulations. So it's not just humans, but there's also, of course, aerodynamics. It's typical thing that you will see from a supercomputer. There's energy, there's molecules, there's bio stuff, waters. What we wanted, so the name we haven't settled so on how we call it, so super nice visualizations. What we wanted was photoreal renders of the data. We wanted to use it for presentations. We wanted to use it for documentaries. We wanted to use it for websites. So this is an effort that is not for short exploration of data, but this is something that they do once or twice in a big project. And the idea is to get maximum impact, so to get a communication that really, really drives through the realism of the simulations, that really makes it to a lot of people, and increases memorability in this way. So how do we need to do this? Well, we know that we cannot use the tools that the scientists use to do visualization. So they use everyday tools which are perfectly good for exploring and analyzing and understanding their data, but they don't have really very good photorealistic output. What we need is to couple to the film industry tools, what they use to do commercial advertisements, to do films, and film industry tools are amazing. They have so much power, so they've been working on creating images for decades now, and they give you a lot of freedom. And the people that know how to use these tools are also very amazing. They really know how to use them. They go really, really fast. And the images on the right were done by people that work actually in the group. So they come from film companies, and they've worked on Transformers, on Game of Thrones. So we work with these people. So we go and hire animators from these companies when they get really burnt out of their fast schedules. You know, if you haven't seen what's working like in the film industry, you don't want to lose too much time on that. They really know how to work on this level of detail. They really know how to work with vast amounts of data and textures and times and supercomputers. So they really have some idea on how we can push data visualization to this edge. We want it to be super beautiful, but it's very important that it's accurate, because the moment we lose realism and we lose accuracy, the scientists usually just click off. They say this is art or an artist's depiction of my work, but this is not true. And they have really, really keen eyes. So when they see these fluid simulations in the movies, they immediately can tell, yeah, but this is bullshit. So waves never do that on the sea or whatever. So an explosion would never have that type of shape. And it's something so fast that you don't see it, but they have trained eyes, so they can really tell. And they shut off, and they dismiss it immediately. So we want to keep on the data visualization side, but also make it really beautiful so that people from the general audience can understand and enjoy the simulations. And for that, we really need to work with them. So we need to be real tight, because even though I do work as a liaison because I have this scientist background and we have other people in the group that come from science background, but we don't know all of the things that they work on. So we have to work with them side by side and make sure that why they use these color schemes, and would this be better, and did we do something wrong here? So we have to do this very carefully. And in order to not lose accuracy also on the spatial and time sense, we have to use their data directly in the film industry software. So we cannot do this. Usually this software comes with simulators for fluids or simulators for physics, this type of engines. They come inside, but they are really, really rough, and they don't show the actual science that you would get from our realistic simulations. So we have to just convert the data into something that the film industry tools understand. And this is a lot of the work, and this is how we started the group. So typical production pipeline in a film is all of that, except for the two boxes circled there in red. And these are the two boxes that make us different. So we do a lot of data processing that these people don't do, and conversion. So what I call data casting is usually, we don't usually have actors. In some of the documentaries, we have people talking, but usually we just use the data to do the communication. So we really need to see how good the data is. So we sit together a lot, we inspect using their software how it would look like, so we create a little bit of a discarding who's a bad actor and who's a good actor in this data sense. And then we have to convert, because data comes usually in numeric formats or categorical formats, but it's never in a format that something like a commercial software will use. And so we started creating a lot of software for data conversions. We can read from many scientific formats. And this is the type of software that we convert into. So Maya, Blender, 3D Studio Max, Houdini, and then different render engines like Arnold Render, RenderMan, Redshift, Blender Cycles. And we're pushing the edge a little bit here because we work with Autodesk, we work with Arnold Render, we work with RenderMan to get their innards of the software that they use so that we can create their own formats and that we can write plugins for them. So we collaborate with these people. We get a lot of return from them. They also give us licenses for using their software in our supercomputer and rendering very fast. So when we use this, you also need hundreds of computers to do the render. And we also can create directly software data in the format that they need. And this is sometimes open information, sometimes they give us these formats, and sometimes we do some reverse engineering of the data formats that they use. And we do this for surfaces, for textures, for voxels, and so on. The good thing about 3D design software, commercial software, is that it's very stable. It's easy to find people that know how to use it. It's a little bit expensive in the case of Maya. It's cheap if you use Blender, which is open source. It's a little bit less stable because it changes too much, and it's not easy to find people that work professionally that use Blender. And then we use many different types of renderers. I'm not going to go into the differences of them, but they are all driving every day to become more and more realistic, which works very well for us, which is exactly what we want to do. Now, by the end, I'm going to show you, if there's a little time, a little clip from what we did. This is not per se a documentary, so another type of product that we create with this are like short technical videos that scientists can show in conferences and presentations or on their websites. This was created for the company Medtronic. They create a lot of devices like pacemakers, and in this case it was a stent for aneurysms, and we created a little video for them. And for this video we use data from simulations on how the stent works inside, and also videos from people doing the operations and getting the stent in place in a simulated environment, so we could get the realistic idea. I want to talk about the previous to last part, the last third track of what I wanted to say. So what is it about data visualization in a more traditional sense? So what do we do there? We started doing videos. We realized we could do these data pipelines very big because we had scientists dumping us like 1 terabyte of data, and we had to create a video out of that. And then we had scientists asking us, how do we extract information from this data? So we started hiring data scientists to do these transformations of the data. And then we realized we were also a data science group. Maybe we could do machine learning for our own projects. And at some point, we also had people asking us, okay, now you have created all of this, but I don't want a video. I want to interact with the data. I want to explore. I want to communicate with an interactive, which is different than a video. And so we have this other type of project where we do this interaction and more typical visualization. So for companies and for our scientific projects, we create interfaces such as this. This is a project for Aguas de Barcelona, again, communicating some machine learning models that we did on how to prioritize the renovation of the piping in Barcelona. And the underlying model has like 400 variables, which translates into about 20 layers of information. So this is a very dense and technical interface. It's not usable for the general audience. It's for somebody who is a little bit trained. The same thing for energy traders. So we did an interface here for a European project called S2S4E. And we have the prediction of whether there's going to be more or less wind than than the average or the expected wind for some season, and it's on a sub-seasonal scale, so it's a new product from the European Commission, Weather Services. This is for a company predicting the flow of ash from volcanoes and the impact on airplanes, on trajectories, and how they can reroute. And this is something we do for fun, so we also do taking the interaction to communicate things for fun. This is something we took also to Sonar. This is an interface showing the relationship between music styles with data gathered from Wikipedia and how people interact with these interfaces. It's very fun because you see them, they are playing around with this. In this case, it was a touch screen, so we'll do a little bit of experimentation. Our research line formally is that we try to improve the usability of data visualization. So we test with eye trackers. You have probably heard of them. They are used a lot for advertising needs, so try to understand how people use different websites. So we use them to try to see which visualizations work and how and what we can do to make them work better. So we research a little bit on interaction. And this is the type of thing that we bring also to this festival, Sonar, to try to do experiments, and that we're going to play with people with virtual reality, data on virtual reality, data on touch screens, data on different formats, sound. So we do experiments there to discover new things. We also do a little bit of communication, like this is a project for the Cuéntalo movement. If you haven't heard about it, it's similar to the Me Too movement but in Spain. It's slightly different, but related. And there was about 2.5 million tweets. We did the analytics for this, and also we did an interactive visualization, which is online. We tried to push a little bit the technology on how to bring many data points and interactive visualization into mobile phones and stuff like that. So a little bit of what makes us different here in the data visualization track of the group is that we use our computational muscle to process as much data and machine learning as we can. We really push that, and when we get this project that have some data that we can extract information or process it, and it takes a lot of effort. And also, the different part is that we do visualization with a lot of testing. So we care a lot about the user and the usability, making it useful and usable. And so we do a lot of testing in our development and deployments. You have seen this in companies, but for academy, this is like totally coming from the future. Another plug for a project that we're working on right now, and we started yesterday. It's a project called Media Portal, and it addresses one important need. We think it's a very important need. So what you see on the left is the Copernicus data store, the climate data store. It's the European service. It's a free service where you can download data, like climate historic data, present data, and all the future scenarios. And it takes coding. It takes a lot of coding. So what we're doing is we're creating a graphical interface for journalists. Try to not to do coding, so they can just create visualizations on the fly. And we're recruiting journalists so that we can do the user testing and make it very good for them. If you know any, just let me know. So finally, I wanted to make a quick tour about the group. So right now we're 16 people, 18 people, and there's one missing here. We have one more animator that just showed up, and then we have a couple new hires. On the top right, for instance, you have Eduardo Graez coming from Chile to do mobility, human mobility. And you will see the backgrounds are very different. So we have people from animate industry, we have UX experts, we have data scientists, of course, we have data engineers. How do we do this? How do we work together? I try to think that it's very important that we really keep together and we really keep working together. This will probably limit us in the number of people that we can have. But I think it's important for the type of projects that we do that we can coordinate and talk to each other a lot. That we don't have like separate teams doing data science and data engineering and UX and visualization. Because the type of projects that we do really try to address problems that have these things really neat together, and they work together. So these four corners where I have design, science, interaction, and technology, this is more or less where the people in the group is now. So we have more or less everything covered. And this is the type of project that we try. This is why we have this. This is by design, so it doesn't happen by accident. It has good and bad parts. Okay, so the good thing is that we have really a large number of heterogeneous skills. And the bad part is that everybody is used to working differentently. So it takes a lot of effort to convince programmers to use Trello or the designers to use Jira or Asana. So it's very complicated to get everybody on board on the tools and the timings and the workflows. The good thing also is, like I mentioned, we can do really, really different projects, a wide range and strange projects. But that's really bad too. So we do really, really different projects all the time, so it drives us crazy. It takes a lot of time to adjust, and many times we have problems that where projects don't sync with each other. So really, we cannot, we never get to do one project after the other. We have to get used to working in parallel with 2, 3, sometimes 5, 6 projects. And this is very difficult to manage and work. So it takes a little bit of effort there. And that's about it. Thank you very much. And I will take all the questions you want. I don't do quantum computing anymore, but if you want to talk about that, that's fine. There's a quantum computing group at BSC. One of the people in my group also works there with them, but I have retired from the area. Yeah.
Thanks for the talk. So my question is, you have different experiences from different larger scale projects. What is the #1 challenge for each data science project you would mention?
The #1 challenge for data projects? Data science projects, you mean? There's 2. One is obvious, and it's predicting the future is very difficult. And this is what everybody wants. And then the other one we have is deploying on actual people's infrastructures. So we push a lot. We get sometimes very good predictions, or at least at the industrial baseline, so we get very good predictions, and they would improve the products. But then there's a lot of IT problems and infrastructure problems and budgetary and timing problems. Getting our software installed in somebody else's facility is usually very complicated. And since we don't work with the same type of client every time and the same type of project, we have to learn from scratch every time. So this is, for right now, our biggest problem.
Anyone else?
Yeah.
All right. Someone?
There's one more. So
one more, yeah, one more. Oh, there you are.
So what's your approach to data visualization in different projects? Do you do the visualizations from scratch, or do you have something which you can reuse across those projects?
Mm-hmm. That's a good question. We have a lot of tools for prototyping that we reuse. Some are commercial, like Tableau. That's the one I like a lot, but the team uses a lot of Python and programming tools. And then we are slowly building our set of tools that we reuse for each project. But when there's a visualization, a special visualization that needs to be unique and whatever, we usually build it from scratch. So we have every time more tools that we can reuse, but the approach is to tailor the visualizations as much as possible to the needs and requirements of the problem. So that makes it also difficult to reuse. So we don't reuse a lot at the really front end part, but all the back end usually is getting better.
And D3, do you use D3?
Yes, a lot. It's our main tool.